Thank you for joining us today for the Consulting Specifying Engineer webcast, Critical Power, Renewable Energy Systems. I'm your host and moderator, Amara Razgis, with Consulting Specifying Engineer and CFE Media and Technology, and I'll be with you for this hour-long education session. If you're having trouble with your slides or with the audio, refresh your browser or click on the Refresh Media button directly under the presenter's photo. If you do need some help, you can click on the question mark at the top right corner of your screen to do some system checks before contacting an online technician. If you do need help, please type a message in the Ask a Question box and we'll respond in the Answered Questions box. To download the presentation slides, use the Event Resources tab on the left side of your screen. Type questions for the presenters in the Ask a Question box on the left side of your screen, and you can ask these questions anytime during the presentation. The Q&A portion will start in about 45 minutes. If you need to adjust the volume, if you can't hear me very well, you can adjust it on your own device. If you're interested in receiving one AIA CES approved learning unit for this event, you do need to pass a 10-question exam. To take the learning unit and to download your AIA CES certificate, use the Learning Unit Exam tab at the top of your screen. This quiz will open in a new browser window, so I recommend you open that tab right now because the link will break when the webcast signs off. In keeping with the American Institute of Architects Continuing Education System Policy, please take a moment to read the quality assurance slide. All right, so here are the learning objectives. We'll talk about these in today's presentation. Please note that any blue underlined text that you see is a hyperlink within the PDF where you can get more information. All right, well, we've lined up two great presenters. They're very informed on this topic. Benjamin Skelton is president and CEO of Cyclone Energy Group. His 20 years of experience in designs for high-performance buildings, from concept through operation, gives him insight and vision for each project. He specializes in energy-efficient and sustainable buildings and is recognized as an expert in building energy simulation, building commissioning, and retro commissioning. Sean Avery is principal and electrical engineer at DLR Group. His experience spans power, controls, and lighting design. He's involved in the design of energy-efficient systems to ensure user comfort, well-being, and effectiveness. He's an expert in early modeling and analysis to inform the development of effective passive design strategies. Both Benny and Sean are Consulting Specifying Engineer 40 Under 40 award winners, and I'm excited to be working with two professionals on the cutting edge of renewable energy. So I'm eager to get this discussion started, but first we want to ask for some audience input so we know what direction to take. So here's the first poll. The question is, what is the #1 renewable energy system you're asked to design or specify? And I'll give you a second or two here to respond. So as these results come in, we have a whole host of different options, and we'd like you to pick the #1 option of what you're being asked to specify. And so far, the clear winner is solar voltaic, but I'll give you a few seconds here to chime in with any other options. In second place, we have batteries, and it looks like in third place, we have solar thermal. So by far, solar voltaic takes first place. So Benny, you're up first. Let's begin with this presentation now.
Great, thank you, Amara. It's great to be here today, and I think everybody's in great luck because the top three are things we're certainly going to cover today. But wanted to first start off by really defining all energy resources that exist out there that are both renewable or non-renewable. So there are non-renewable sources that we're familiar with. These include coal, crude oil, natural gas, uranium or plutonium used in nuclear energy. These are, the using resources from the earth and definitely not considered renewable at all. Now, there are even more renewable resources that we can choose from. We have hydropower, solar, wind, geothermal, biomass. These are things that can be made from wood, wood waste, solid waste, landfill, even methane. These are often found in farms and places like that. There's tidal power, ocean thermal is an option, and then crops are used. You might see this through ethanol. Corn is a renewable energy resource as defined here. So when we look back at how energy has been used in the United States, at least throughout the past 70 years, you can see that by far the most prominent source of energy production in the United States has been coal. We've seen a very, very sharp decline of that since the year 2000, and we've seen, conversely, a very sharp increase in natural gas consumption since then, moving up to present day, as of 2020, being almost 40% of the total energy produced. Renewables are sneaking up there as well. You see that starting in 2010, that climb has started to shift and they're moving up, and that's going to continue to grow while coal continues to drop off. As projections look, these graphics are from the Energy Information Administration, so it's an open source website where you can get almost up to the date daily information on the energy markets throughout the United States. So, looking at the total percentage as we project out to 2030, 2050, a lot of cities, jurisdictions, states, a lot of different organizations have goals set around the years 2030 and the years 2050 for carbon reduction, and renewables are going to play a big role in that, especially in the building energy consumption world. So we see that 44% of the power generation needed in the United States in the year 2050 is going to come from renewable energy, while natural gas will be about the same. You can see it grows because the amount of energy production will need to grow. And they're predicting nuclear to stay relatively similar to where it is or less than it is now, and coal to fall off, to continue to fall off the map. So as we look at where sources of renewable energy are going to make up that mix, an overwhelming percentage of that is going to come from solar. Currently, it's not that. Solar is not the highest producer. Right now, wind is. You might see a lot of large wind generation farms. If you're going to coastal areas, you're starting to see offshore wind production, and that's all in the works to get increased between now and 2050. There are significant efforts through government funding, through administrative planning to try to get more large-scale production. But as we look at it on a building level, what can we do? Solar is going to be that place that's going to pick up. Now, there's been a lot of news about grids, infrastructure, and resilience. And grids and infrastructure resilience, these all kind of tailor towards things around potentially climate change or the need that we need to have a more secure infrastructure in the United States to secure our power. There's talk about how renewable energy can make our grids unstable. And so finding ways to make the grid stable and balance the renewable energy is a very important part of the equation going forward. But we saw just last year, the Texas power grid failed during a winter storm, unseasonable winter storm, took the entire state down and cost billions, trillions of dollars worth of damage to buildings and infrastructure there. Recently, there's been talk about Lake Powell, a very large hydroelectric producer, actually reaching a critical low point to where it wouldn't be able to produce hydroelectric power, impacting something like 5.3 million users. There's already been some hydroelectric in the West that's been shut down because of the drought and the low water levels. On a conversely interesting note, the state of California was briefly fully powered by renewable energy last month. There was a brief moment where they produced more energy than it actually consumed, but at the same time they did this through renewables. They still had to have sources of power such as natural gas online to provide that bulk power. But things are changing. They are starting to see the infrastructure, and they're starting to see the production increase there. And one thing that's come up, I think the question of what you're being asked to design comes around solar photovoltaics. Just recently, there's been a lawsuit and some investigation around solar providers, mainly out of Southeast Asia, to see if the market is fair with U.S. markets. And that's caused the production or the use and installation of solar panels to slow in the United States. So there's a lot of factors that come into play when we look at these renewables, but I think we're just at the cutting edge of this, that things are going to get to a place where production is more linear, and you can see from the predictions, the estimates are looking that way as well. When we look at buildings, what really makes sense? And I brought all the renewable sources back to the page here, and kind of poorly highlighted the ones that do make sense. But hydropower, this is a utility scale source of renewable energy. It's not really practical to provide hydroelectric generation on a building site. It takes a great level of water pressure to be able to turn a turbine and generate electricity. So we see that at a big utility scale. Solar and wind are the two applications that are site-specific and building-specific that make the most sense. They can be put on a building, they can put next to a building, they can be put on the site. When we look at geothermal, this can sometimes get confused in the building world as being the geothermal systems that are used for heating and cooling. This is not the same. That's actually referred to as geo-exchange, and that's using the earth as a temperature source to both store and reject heat energy to. While that seems renewable, it's not a source of energy generation. It's purely a way to store and reject energy. So we call geothermal as more of actual energy outside of the earth coming up and generating that power. So we see this in very volcanic areas where there's a lot of energy in the earth. Biomass, I mentioned, this can be used on the building scale, but it tends to apply more towards campuses. When I've seen this done, it's in healthcare campuses or large building campuses where they have central utility. And this might be a place where they can fuel switch or source fuels from different places. But biomass is certainly something that has come up since the early 2000s. And while it does have some emission factors to it, there are ways to work around that and to minimize the impact of that. Tidal power, again, is a utility scale source of energy. This is going to be something off of major coasts to be able to generate that energy. And ocean thermal, obviously, is also a utility scale thing. We don't see as many of these. They're very expensive to build. There's often a lot of restrictions about environmental restrictions around these types of sites. So we see that really in the utility world. And again, crops, using things like corn for alcohol production as a boiler fuel. These can be used in a campus scale. Usually it takes very specialized equipment. You can get it for household scale too, but it's not one of the more common applications of renewable power. And a lot of times when we see the household scale, it's not necessarily having the clean emissions factor that we might have at a larger scale application. So focusing in on wind energy on a building site, this can be complicated. To get a wind energy to work, you need to have a cut-in speed. So often that's around 5 miles per hour of a constant wind speed before you start generating any energy. The mechanisms in it to put them on a site, they tend to be smaller. They don't generate a ton of energy, but they can be used. But a lot of times you need to have that constant source of wind. Wind falls off a lot of times at night. It isn't a great source of production there, but it is something that can be used on site. You do run into some things like local ordinance restrictions where you might not be able to put it on site. There's concerns about putting large wind turbines like utilities use on sites because if it fell in a windstorm, does it fall on your property line? We've seen issues around that. So wind has its challenges. At the small scale, it's a low producer. At the larger scale, like you see with the utilities, it's a great production source. And that leads me into the other good application for buildings, which is solar energy. Solar panels can be put anywhere. It's just how much energy are they going to generate? And I think there used to be a time when we looked at solar panels and said, well, we can only do it in the southeast or the southwest or the south where there's higher incidence of sun exposure, less cloud cover. But those times have changed. Solar panels are much, much more efficient than they were even a decade ago. They could produce a tremendous amount of power and on a single cell, and they have the ability to produce with light cloud cover and things where they might not have produced in the past. So necessarily the map isn't restrictive anymore, and it can be beneficially applied to buildings almost anywhere. And solar energy production is great on buildings. You can apply it to a roof. You can keep it on carports. You can put it in places that you might see as a marketing tool for an office, but you can put it on your home. So the solar panels can be installed. Our next presenter is going to go into a lot more details on that installation, but it's very good for building infrastructure. It can tie right into your building systems as well. Real briefly, there are several types of solar photovoltaics out there. The most common, the highest efficiency rating, are monocrystalline type. These are what are manufactured most commonly. They're pretty readily available. They have great durability, can last 25 years, typically under warranty for 25 years. They tend to be one of the higher cost installations, but they are the most common on the market. When we see the polycrystalline, these are interesting. They have a different color to them typically. They're made of crystalline that's a mixture, so it's slightly less efficient than the monocrystalline. And they tend to be kind of the medium cost. They have a pretty good durability to them as well because of the different uses of the different crystallines that are made up in the components. And the last is thin cell. These are the least efficient of them. They're made from several different types of things. They can be made from amorphous silicon, for example. The benefit of this is they can kind of be made into patterns, and they can be used to look anywhere that you want. So you see a lot of thin film applied to window surfaces on the sides of buildings, or you might see them put custom glass. They tend to be a little bit more for show, but our recent experience with them is they can have great performance value to them, as well as a good marketing value. They are the highest degrading photovoltaic film that's out there. They don't have nearly the life, and they aren't warranted for the 25 years. It depends on the material that you use, but you might be looking at 10, 12, 15 years on some of these products. And as far as the production of it, like I said, there's different looks of it. You can do a different type of feature with wind and solar. So solar, you don't necessarily have to have it at ideal angle. It can be flat mounted. It just won't produce as much energy as it were if it were put at an optimal angle towards the sun. There are solar panels that can track the sun. They would add costs, but on a large scale, that might be beneficial. On a building scale, that's not always the case. And then there are some ordinance restrictions that come with how you install solar panels on your roof that you have to be aware of. Fire department access. Sometimes you can't put a full roof array in. You need walk aisles for the fire department to not get electrocuted on the roof during an incident. So there are a lot of different things that need to be taken into account. Are there neighboring structures that are shading the building? Are there trees? When you look at all of these, there's a lot of limitations I can take into account, but in general, the solar market has gotten to a place where it's very applicable in the building environment. And I think, we've used them a lot to get towards zero energy. So I think I'll hand it over to Sean to talk a little bit more about that.
Thanks, Benny. Hey, so to start off my portion of the presentation here, I figure it's good to level set in a couple definitions first of some phrases I may drop throughout the presentation, because there seems to be lots of nets and lots of zeros that we talk about when we're discussing these things here. So net zero can be defined in a handful of ways. Today, I'm going to use it as net zero electrical energy. I won't be talking about carbon or anything like that, just net zero electrical energy. Net metering is the term used for being able to spin the meter in both directions. That's going to be in agreement with the utility for that point of interconnection to the solar system. A net producer would mean that you are producing more than energy than your building would consume if you're attached there. This is generally not accepted under the guidance of net metering. There's been talk over the years of, they'll pay me for the excess energy I produce. Yes and no. They'll generally allow you to produce up to amount you use in a year, but they're not usually going to write you checks for excess you do. It may vary, but generally that's the case, is that you want to not really exceed your consumption in a net metering scenario. Zero feed-in is a situation where you won't be allowed to net meter, and you need to store and use all that energy on site. We don't see a ton of that right now in the US, but we're starting to see it in places like Hawaii, where they're starting to get to the point of maximum solar penetration on their grid. So anyway, I will use those terms a little bit throughout the presentation here. A couple more, grid interactive. These are going to be inverters that are grid following and will just kind of go along with what they see the utility grid doing. And off grid, you need something that's grid forming. So they are going to create that 60 hertz signal. So you need that piece in any off-grid scenario, or like Benny mentioned earlier, in California, still needed some conventional generation to be the grid forming piece there, since so much of the solar is mostly just grid following. Then microgrid or hybrid systems are systems that can switch between the two, grid interactive and off-grid. The basic pieces of any solar system are shown here. We'll start with our PV modules. We're all probably familiar with those. On any commercial building, we'll probably have hundreds to thousands of those on a rooftop array or carports, whatever. To the right of that is a rapid shutdown device, or maybe an optimizer. For rooftop solar arrays, we need to comply with some rapid shutdown codes. And so we'll generally have one of these for every 1 to 2 modules on the rooftop. And they use a communication protocol in the inverter to contain the electricity within the module, or within that device, basically, and the system gets shut down for fireman protection. To the right of that, we have some examples of some solar inverters. These are converting the DC electricity to AC electricity that's needed for the building to use. Most predominantly, I see string inverters, which is example on the top, and I'll show you sort of a wiring diagram of this in a minute. But they're generally in the scale of 25 to 100 kilowatts in size. And then below that is a micro inverter example, which would be used for, again, every 1 to 2 modules would have its own little inverter there. And there's pros and cons to each one. And then finally, once you go there, you usually end up with the utility disconnect before you tie into the grid. The requirements of that vary a little bit by jurisdiction. Most often, if they are required, the utility wants you to have a viewing window on it, as shown in this picture here, so they can visibly see that the system is disconnected if they had to go in there and do any maintenance. Here's an example of a one-line diagram for a string inverter. I'm not going to spend a whole lot of time here, but I want to make out a few points on here. So we have our solar modules, which produce a DC voltage of 50 volts plus or minus 10 volts there, just depending on the configuration. And generally what we'll do is we'll string them in series, kind of like Christmas lights, up to a point where on the DC side we're achieving voltage around 1,000 volts. So in this version here, it's probably a little hard to read, but I have 18 modules in a string. Then I'll start paralleling those into the inverter. So in this example here, again, I have 10 strings connected to this inverter, all in parallel. They're broken into 3 groups, which connect to what's called a multiple power point tracking zone. For the sake of this conversation, keeping it simple, those are basically optimizing the power of the strings that are coming in from the solar there. So the energy produced by the PV modules they're kind of a dumb device, and they need to kind of be optimized to maximize the amount of power being pulled out of them. So the different MPPT zones here will allow for different orientations. This one here has 3 zones in it. So that might be able to allow for 3 different orientations of the modules, or allow for shade tolerance. The microinverters I showed earlier would do that optimization at the module level.
All right, so let's look at another poll question. This next one will give us a little bit of insight about challenges. So please define the biggest challenge when specifying renewable systems. So the second poll has fewer options to answer. So if you could let us know what your challenges are, that would be fantastic. Let's see. So far, we got some. Oh, yeah, one jumped up here. So first cost to purchase and install is the number one challenge. About 40% of the audience has said that is number one. And then number two is utility requirements. That is the second biggest challenge. And the third biggest is codes, zoning, regulations. We've talked about that a little bit. So let's move on to the next portion now that we know that. Thank you.
All right, so based on the questions I got from the group going into this, I feel like the best way to kind of cover everything is to sort of do it under the guise of solar ready. And I'll cover some retrofit items and such as we go forward here too, but I'm going to frame most of this conversation in and around solar ready. So the way I like to do this, if I'm working with a group, a project team or whatever, is answer the following questions on the list here to sort of build some project goals that we can all agree upon. Sometimes, like you see at the bottom here, those goals might already be defined for us if it's in, if you're under the IECC, for example, and have the solar ready requirement there, or certain state requirements such as Cal Green. Those might provide the answers for you for some of the questions already that you need to go around. But you might be working on a project that might be exceeding the code, that might be a net zero building. And so I usually like to start with these questions here. So for example, how much solar are we going to need? Where's it going to go? Where are we going to put it? How will we support that? And how can we make future implementation easier, even if you're going to do solar now, like as the project is proceeding, you still kind of need to answer this question. And then how will we get the electricity all the way from where you're putting it to where we're connecting it? And then finally, all the nitty gritty about interconnecting into the electrical grid, whether that be the code requirements or the utility requirements, came up there in the poll. So how much? How do we determine how much if it's not just defined for us by the code? So again, we need to first figure out what's the energy goal for the project. Is it net zero? Is it a percentage offset that you're trying to achieve of the energy use of the building? Or is it more space-based, like for example, in the IECC, that they want you to use 40% of the roof? So if we get a number, let's say we're doing a 15% offset or something like that, then we need to sort of know that energy amount that we're trying to offset there. So for existing buildings, this is pretty easy. We can use meter data. For new buildings, generally you're going to have to use an energy model to achieve that, which usually spits out an energy use intensity or an EUI, which you can convert to kilowatt hours and get close on the size of system you need. The other piece of information we need to know is how a system in our area will perform, what 1 kilowatt of solar will produce given the orientation and the location of the installation. And so that we'll need to use calculators such as PV Watts from NREL or other software such as PVSYST or Helioscope is an example. I have a web-based one in the upper right corner there. And so this will tell us, we'll model a system in there and it will say for every kilowatt of solar you install, it's going to produce 1,500 kilowatt hours annually, something like that. So from that, we can solve for the PV system size we need. Knowing our energy goal, we can divide that by its performance and get the nameplate rating-ish for the system size that we need to target for the installation. Next, we need to consider where that's going to go. The image I have here is from a site visit I did a while ago where I had I looked at about 15 different schools to determine which ones we wanted to put solar on. Many of them were brand new and considered solar ready, including this one right here. And this was well before requirements were listed in the IECC or anything like that. This building did not get solar because, as you can kind of see, my question would be, where are you going to put it? The cleanest area to put an array would have been north of the penthouse, which would have been in the shade the entire time. The penthouse is littered with a forest of fall protection anchors. And on the right, there's just a lot of obstructions that either cause shading or just don't give you a good area to put solar array. So the definition of solar ready for this building was literally a conduit up to the rooftop. The next building, and this is kind of a spoiler alert, this one was a good building solar ready wise because we ended up putting solar on it. This one had a nice clean rooftop that had very few obstructions, had a pathway from the electrical room up to the rooftop already appropriately sized, and it made a very easy solar installation in the future. So at this time, when I went through this, I realized that there wasn't a good definition for solar ready, and that there's a lot of room for interpretation on what that meant. I think it's getting better, like I said, with the IECC right now, but still at some point, we need to answer those basic questions. If you're looking at a flat roof to put solar, you're going to end up with most likely a ballasted system, similar to the image on the right, upper right there. And those will be sloped between 5 to 10 degrees. I think I had my greater than sign in the wrong direction there, but typically 5 to 10 degrees is what you're going to have for the solar modules there to maximize the density of the installation. Because the greater the slope there, the more inter-row shading you're going to have, and the further apart you're going to have the modules. With that, you're going to end up with about 13 to 15 watts a square foot. So now that you know your system size number from the previous question, you can kind of calculate a rough area you're going to need to support that array. Again, this is a ballasted system, but I want it to be clear that just because it's a ballasted system does not mean you're going to get away without mechanical anchors. Mechanical anchors may be required due to seismic areas, due to shifting of the array. It may be required due to wind uplift, especially in the corners of the array. And this is usually calculated a lot of times by the racking manufacturer. I had a client once think that he was sold a ballasted array and there'd be no roof penetration, and was frustrated to see a bunch of roof anchors on there. That being said, the roof anchors now have been got to the point now where, like in the image shown in the lower here, there's they usually come pre-made with the type of roofing material to match the roof of the building, and so they can easily be screwed on and then welded in place, or whatever the other method that you're using depending on the roof type. So it does not mean necessarily that you're just poking a hole in the roof. It's pretty more like a little more sophisticated than that. Structural standpoint, you need about 5 pounds a square foot is kind of the general rule of thumb for a ballasted array to support it. The other thing to consider, if you're in areas where you have significant snow, you'll need to worry about snowdrift zones as well during the wintertime. Again, for the area calcs, we also need to consider the fire access, which Benny had mentioned earlier, and that generally consists of a 4 to 6 foot pathway around the perimeter of the building, depending on how big the building is. Larger buildings require 6 feet. If they're less than 250 feet on either axis, it's 4. You'll need center access pathways to the building. And in addition, every 150 feet square, roughly, you need to break up the array to provide venting opportunities in the case of a fire. The image I have here is a really large building, and it's a little hard to see all the pathways, but you can sort of see how I've had to break up the array. This example, though, is relatively easy. It always ends up being a game to sort of determine how your building fits the general guidelines of a flat roof box, because many of the buildings we deal with are not that. So that's one thing to consider is know this is what the code says and kind of how that gets applied to your building that may not be a flat roof square or rectangle. For a slope roof, I always suggest if we're doing a slope roof to try to use a metal standing seam roof. It's the easiest one to attach to. You don't have to have roof penetrations for every anchor, which probably need to occur 6 to 8 feet on every rail. You can use clamps such as the one shown by S5 there to mount the racking through. They just pinch the seam, and so there aren't any penetrations other than your electrical on that rooftop. Because you don't have to worry about inter-row shading, you can get a higher power density on the roof. So you're looking at 17 to 18 watts a square foot. And in addition, you'll need to consider some setbacks per the IFC2, about 3 feet around the edges there. If you're going with carports, please check your local adoptions and addendums to the adopted building code, because they all have a little assumptions in here in and about the maximum amount of size array can be and the spacing requirements for those. You may end up having to do sprinklers if they get too big. And there's different things for fire truck clearance and the like there. So please check your local code adoptions for those. For solar, for ground mount, again, we're going, you might be able to have a smaller array to achieve the same amount of energy production, but you're going to probably take up more area because of the row shading. So you're looking at about 10 watts a square foot. You probably have a fixed tilt. Maybe you can get into the tracking system, and you also want to consider a fence around the array as well, just to keep people out of it. Finally, where's all the equipment going to go? Is it going to go up on the rooftop? Is it going to go on the ground mount? And so these are just kind of some things to consider along with that too, whether you're doing rooftop array or carports and the like. So here's a quick example calculation that I went through. I have a building that's 50,000 square feet. We assumed energy use intensity of 25. So we calculate our energy use both in kBTU and kilowatt hours per year. I modeled a couple different arrays at 5, 10, and 15 degrees to kind of get their production factors. And so I was able to take my annual energy and divide it by those to kind of calculate the different array sizes I would need to support that. Then taking it from there, I would figure out the area I would need for the different arrays as well too at the bottom. So again, going for this, we want to set up for success. Don't do that. Go through and just be mindful of where you're going to put it and set up whether you're going to do the solar now or in the future. Take all that into consideration and prepare it for an easy solar installation in the future. For the electrical pathway, you need to consider how you're getting from the rooftop down to the main point of service or the point of interconnection while during the building design, ideally there, and then make sure your conduit is sized appropriately for the system as well. This is also in the IECC. You don't necessarily need to connect all the way to the gear, but at least have that point A to point B planned, and likely that utility disconnect as well too. So you need to kind of understand the utility requirements and where that disconnect needs to go, because that's where you're trying to get back to also. From the interconnection standpoint, this is covered in Article 705.12 in the NEC. I could easily spend an hour on this topic, so I'm going to race through it a little bit just to give some general guidance. The smaller the system is going to lean towards a load side connection, meaning you're on the load side of your main service disconnect. And the larger size is going to go more on the supply side. For the load side disconnects, the most commonly used one is the 120% rule, which means I can locate my service, the PV point of interconnection at the opposite end of the bus bar from the main service disconnect. And if I sum those two up, they cannot exceed 120% of the rating of the bus. Another way around this one is you could either upsize the bus compared to the main breaker or reduce the main breaker so that it's smaller than the bus. And then the sum of those together can be 100%. And then you can put the solar anywhere on that bus that you like. These are the easiest ones in a retrofit. And if your system size is relatively small compared to the service, it's the most easy to implement. For larger systems and you're going line side connection, you're allowed to have that PV system size could basically be up to the rating of the bus. Some clients now are going solar ready in this fashion to where they're adding a solar connection cabinet, for the example on here, to where when they install solar, they don't have to shut down their main building service. This allows some other complications, though, too, of what happens if your system is significantly smaller than, in this example, 4,000 amps. You're going to have to somehow size everything down in the future. And then in more of the retrofit standpoint, you might have to do a custom bus tap where you drill the bus if you don't have enough existing lugs on the supply side of that disconnect. And this will require a UL listing, a relisting of the gear generally. And so what this will look like is you'll probably have to go to a consultant, and they'll come out and take measurements and determine if and how that thing can be modified to supply the existing stuff. And then they'll come out afterwards and bless the work that's been done and relist the gear. I know we're getting close to time here, so I'm going to start burning through a couple of these other slides a little bit. Finally, check on your utility standards. They all have something that's a little bit different depending on the size of the gear, whether or not you need a production meter, any advanced controls or remote terminal units, especially in areas that are getting more heavy in solar, like the Southwest. So really read through their documentation and understand what they need there to comply with their requirements. Finally, if you're preparing a solar-ready deliverable, my recommendation is, again, on a roof plan with their architectural electrical, show the proposed area clearly. You don't have to do a layout necessarily. On the electrical plans, clearly indicate the pathway from the rooftop to your point of connection, and also show that on your single line diagram. And finally, a performance spec along with that to indicate your intended function, the system size, and all that there. You don't need to do full construction documents because every different module and inverter combination requires its own different engineering there. Quickly, moving on to batteries for a little bit. There's a lot of reasons why you might install a battery system. Maybe it's a state energy requirement, for example, that's coming in the next round of Cal Green. And I'll go through a quick slide of some of the different reasons why you might want to do that. The industry is still young. The markets are still developing in this area, and codes are still moving quickly. The tech right now is mostly lithium ion, but there are some other options out there like vanadium and such like that. The things to focus on in batteries right now is the locations you're putting them, and the listings of the battery systems are critical. So UL 9540 and 9540A are the two main listings you want. 9540 is really the battery system operation and fire requirements, and 9540A is a flame spread test that you'll really want to have if you're going to be in, around, on, or near a building. Right now, the IFC and the NFPA 855 are the two codes that are kind of bouncing back and forth along each other to trying to build the requirements. They vary slightly, but they're usually kind of incorporating each other's ideas into that over the long run. The handful of different reasons why you might want to use a battery system. There's a lot of information on the slide, and I hope you'll have a chance to look at it all later. But it might be for resiliency, if you need to maintain a microgrid in case of power outages. Again, if you're in the Hawaiian market or somewhere similar where you're not allowed to backfeed the grid, you need to use battery systems to store that excess produced by your solar system during the day and discharge that at night. If you're in an area where you have great demand charges at certain times a day, you're going to be in the demand management column here, where you're charging at nighttime and then discharging during the day to lower the peak demand of your building when rates are really expensive. Demand response is similar to that. It's just maybe your utility has a program that says, turn it on now, we need your help. And finally, I have carbon arbitrage. Sometimes it kind of goes hand in hand with demand management, but there might be times a day where the carbon, the amount of carbon per kilowatt hour is greater, and you want to reduce your carbon footprint. So you might charge the batteries when the carbon is low and discharge when they're high. An example of how this all plays together, if you were to tie this together in a net metered system. This here is sized for a basically a net zero energy building. The red curve, I know it's a little tricky to see with it all going on at once. The red curve here is the existing building demand over the course of a day. If we add net zero solar in here, that's the pink curve and how it produces the energy there. This is actually in the California market, where right now the peak demand time is not during the middle of the day anymore because of all the solar that's in the state. They've shifted that now to the evening from 4 p.m. to 9 p.m., which is this yellow rectangle. So really, you see that solar does not do a good job of assisting in reducing your demand during that time frame anymore. It drops off to zero during that time. So that's where the batteries come into play. The blue line is the battery function there, where we're charging at the left of the screen in the green area in the middle of the night. And then when we hit that on peak window there, the batteries start discharging to help assist that demand lower even more. And the net result is the green curve.
And Sean, when looking at zero energy buildings and sizing these arrays, you have to understand what those loads after hours are too. A lot of buildings, when you get in the commercial realm, aren't necessarily 9 to 5. You might have a refrigerated facility, or you might have something with 24-hour operations, a data center, like a mission critical facility. To size those for zero energy, you have to have some significant overproduction during those peak hours to be able to handle not just the shifts at the evening and the morning, but also overnight.
Yeah, thanks, Benny. Yeah, this curve here is a pretty simple building. It's an educational building, which is no one's around in the evening and everyone's around during the day. But yeah, thanks. That's a great point, Benny. Finally, in a microgrid scenario, again, I could probably talk a whole presentation about doing microgrid setups. Again, I mentioned about following a grid forming. In the microgrid, we need to have a grid former as we disconnect from the grid and isolate the building or portion of the building. And generally, that's usually been the best system. Maybe you have a generator that does that. And the other thing I'll talk about here is grounding. And that's make sure to keep track of your system grounding, much like you do with the generator, whether you're doing 3-pole or full 4-pole switching, to make sure that you maintain a system ground. I've seen issues before where that's not been maintained properly, and so there's been some issues with some single phase loads. Usually in these scenarios, the controls are done by the best manufacturer or assembler. And so when you're designing these, many times I've mostly just written a sequence of operations and coordinated with at least the basis of design manufacturer for the system to put that together. But usually the best manufacturer is packaging up that system and providing the control system. Coming near the end here, just a quick slide on costs. These are rough ballpark costs that I've seen in the market lately for the cost of building the systems. Rooftops are coming in $2.75, $3 a watt. Your carport arrays are more expensive because you're building more structure to support them. Canopies, this would be something similar to that, but maybe on top of a parking garage where, again, you probably have even more structure. And ground mount arrays are generally the cheapest right now. The battery energy storage systems, they're estimated. I might even say this is a little bit a year old now. I think about $1 per watt is really, plus or minus, is really what they're kind of coming into right now. But it also really depends on availability. Like I said, the market is still young. Benny, you want to cover the PPA?
Yeah, thanks, Sean. So there's lots of different ways what Sean's talked about could be applied to the design of it, but how do you actually purchase it? Who owns it? Who puts it on the building? So we see the purchase, where you purchase the equipment, you design it into the building, you put it on your building. You're maybe taking advantage of that, earning the federal tax credits and rebates, local incentives from a utility company. But then there are other options where someone else who owns the array can lease it back to you. And that's probably one of the least common. But then one of the more common ones that we do see is a purchase power agreement, or PPA. These are typically over the 25-year life of the solar array, and it's where a third party actually owns, designs, and installs this and sells you back the electricity at a different rate. So pretty much you're putting a utility on your building, but you're not responsible for the upkeep of it, the maintenance of it, and you're able to take advantage of the use of that. So the purchase power agreement is certainly something that we see applied when it comes to people who want to take advantage of putting the equipment on their building, but not necessarily have the responsibility for maintaining it or operating it, and can take advantage of the reduced utility rates. But the purchase is one of the most common one. We mostly see people purchase these arrays, but the PPA is certainly another big option out there.
And finally, I get a lot of questions about maintenance and lifetime for these systems right now. Most PV modules are warranted for 25 years, but they'll probably produce much longer than that if you let them. They usually just degrade about 0.35 to 0.5% a year in their amount of production. So 25 years usually ends up being, well, I think 20 years is 80% there. Standard warranties for inverters are 10 to 15 years. They can be extended, but here's the electronic piece in the system, and we know electronics do have a lifetime. So, for example, most PPAs factor in an inverter replacement about halfway through the agreement period, if it was, say, 25 years. And for battery energy storage systems, they're usually warranted for about 10 to 20 years too, depending on that. And so if you were going for a full 25-year PPA, for example, there might be a battery replacement worked into that too. But many of them are warranting their systems for the full 20 years. So your maintenance on the system, again, inverter or battery replacement, you might have to replace failed modules every now and then. Cleaning the modules to maintain your max production is something that's would be done frequently. And then anything else would be anything to do with the communication systems for metering the system, whether that's wired or cellular, and potentially anything to do with the thermal management system for the BESS, although that should be covered under the BESS warranty if that was going to be the case. I think that's about it.
Yeah, nice. Thank you, Benny. Thank you, Sean. That is a lot of information to take in. And as a reminder, you may earn one AIA CES approved learning unit for this event. You do need to pass a 10-question exam, and to take that exam, you can access it under the Learning Unit Exam tab. It is at the top of your screen, and it does open in a new browser window. And quickly, just wanted to let you know that we have more education. A course just started yesterday on how to engineer for future-ready healthcare buildings. So check it out, very related. All right, gentlemen, we are going to take some questions. We have quite a few. Again, if you do have a question, you can direct it to one or the other presenter. But Benny, I'm going to start with you. All right, so electric boilers is really what we specify for renewable, since we buy renewable energy credits for our electric power purchases. Could you comment on that, Benny? Hey, Benny, if you can make sure that you are off mute,
yeah,
we can hear you. Thank you.
Now you can hear me better. Sorry about that. How you if you're going to put renewable energy on your building, it's typically going to be electric. Solar is producing electricity, so having a natural gas source of heating is probably not going to be your most best way to offset reductions. So as we look at carbon reductions, carbon neutrality designs of buildings towards that, you're going to want to be putting electric equipment in your building to offset that. And so yes, electric boiler is a good option. They're probably not the most energy efficient because they're 100% effective at producing electricity, as opposed to something like a heat pump that can produce 2 or 3 times as much heat per unit input. So as we look towards carbon reduction and solar designs, we're going to want to put more designs on that have efficiencies like a heat pump. So I think that's where our designs are starting to move towards.
Okay, great. Got it. And if you do have questions, please type your question into the Ask a Question box and type the presenter's name so we know who to direct it to. As a reminder, you can download the presentation slides in the Event Resources tab on the left side of your screen. So Sean, I'm going to direct this next question to you. We're talking about IEEE 1547 requirements here. So what are those 1547 requirements for interconnection and common utility requirements?
So I'm going to pair that IEEE 1547 and UL 1741 are roughly, I think they are pretty much the same thing in terms of requirements. And generally, a utility is going to require that your inverter, whether that be for your solar system or your battery system or wind system, has that listing there. Because that basically tells them it's safe for grid interconnection. And the main things that covers is there's protection scenarios in there for undercurrent and over frequency and under frequency, and the whole gambit of those different protection scenarios are very well spelled out in there. And there's a few other things in there, such like an IEEE 1547 inverter must see the grid for 5 minutes before it can interconnect to the grid. And then if the grid drops out, it's got to disconnect immediately and stay off until, again, it sees a stable grid again for 5 minutes. So there's operational stuff and protection schemes that are spelled out within that. But generally, if you're doing grid connected, you want to make sure you have that UL 1741, which encompasses those IEEE 1547 requirements in it.
All right, thanks for that info. Benny, another question over to you. What's the physical dimension of a typical solar panel?
Well, it's going to depend on what type of solar panel you go with. They can come in a variety of different sizes. And if you're going with a thin film panel, you can design it to be whatever size you want. When you go to more of the mono or polycrystalline style, they tend to be, or have historically been around 5 foot by around 3 foot or so, 18 square foot in dimension. But lately, we've actually seen the 540 watt panels closer to like a 28 square foot. And again, the dimensions can be all over the map on that, but they're getting much, much larger as a single panel. Like a single panel at 540 watts is pretty impressive on a commercial scale.
Right, yeah, it is. Thank you. All right, Sean, another question for you. So this kind of goes back to what you were discussing toward the end of the presentation. Are you saying it's a good idea to charge batteries at night from the grid rather than during the day? What are the pros and cons there?
The example I gave, and I did go through it very fast, was a specific example where the energy is really expensive in the evenings, where solar is not helping you offset that energy. And maybe, I guess, and the energy is still, I guess, a little bit more, is cheaper at the evening. So it really depends on the rate structure of your utility there. It's going to be different everywhere. I'm looking at a similar thing right now, and the example I showed was in California. I'm looking at another area, and California's example does not work at all in the other area. It's completely different. So it really just depends on what the rate structure is of your utility, and again, exactly what you're trying to accomplish there, whether it's a zero feed-in where you're going to be charging that with the solar during the day, or maybe you're just trying to put batteries in standalone without solar to offset your demand, at which time you're charging at night.
Sure. Okay, got it. It looks like we have time for just one more question. And Benny, I'm going to send this one over to you. Is the PV market experiencing supply chain issues? And what kind of delivery times are you seeing with this?
Yes, that is correct. The supply chain is having delivery issues. This goes to a fair trade lawsuit that's under investigation right now that is scheduled to be determined sometime in August. I don't know if that's going to get expedited due to some complaints, but it is certainly halting a lot of projects or putting things in their place. But it depends on where you're sourcing those materials from. We're still seeing delivery times in the 6 to 8 weeks range currently, depending on people are sourcing it from a U.S. manufacturer or Canadian manufacturer. It tends to really be affecting mostly the Southeast Asian manufacturers, which are by and large a majority, but we're still seeing people able to source things, and the costs haven't been able or haven't been escalated as such. But I think that'll probably change if this review doesn't get expedited a little bit.
Right. Okay, well, lots of great information and definitely not enough time. I would like to thank these extraordinary subject matter experts, Benjamin Skelton and Sean Avery, for sharing their extensive knowledge of renewable power systems. And now we do want your feedback to improve future education sessions. A couple of questions will pop up on your screen as soon as this webcast ends. Please take a few seconds to answer them. And finally, on behalf of Consulting Specifying Engineer and CFE Media and Technology, I'd like to thank you for joining us. We'll see you again at the next education session. Thank you and goodbye.